the sort of formal part, I guess, of the session today. So I'll do a quick intro. So yeah, thanks everyone for joining. So this week our speaker is Catherine Espaillat from Boston University. And one second, sorry, the YouTube, as happens every week, and I just don't remember, starts talking back at me and I can hear myself. Anyway, I'll start that again. So yeah, our speaker this week is Catherine Espaillat, who's an expert on young stars and how young stars and planets form out of protoplanetary disks, which she pursues with a multi-wavelength observational approach. So Catherine did her PhD at the University of Michigan before moving to the CFA at Harvard for a postdoc, followed by a Sagan Fellowship, and then hopped across the Charles River to take up a permanent position at Boston University, where she's now an associate professor. So today she will be talking to us about multi-wavelength accretion variability in young stellar objects. So Catherine, again, thank you very much for agreeing to speak to us, and it's all yours when you're ready.
Sure, thank you. Okay, so thank you for the invitation. I have my chat room open. I'm used to this by now, so if you have any questions, just pop them in the chat room throughout the talk or hold them to the end, whatever you prefer. But you're free to ask questions whenever. So yeah, so like I said, thank you for the invitation. I'm going to be speaking about young, roughly 1 million year old pre-main sequence stars that are called T-Tauri stars and their surrounding protoplanetary disks. So T-Tauri stars are accreting material from these disks. And while accretion is a common astrophysical process, we still don't understand how it occurs. And here I'll be discussing how can we try to better understand accretion, particularly in T-Tauri stars. And I'll be using multi-wavelength variability observations of accretion and seeing what this can tell us about the connection between the young star and the innermost regions of the protoplanetary disk, as depicted here in the first slide. Okay, so why should we care about accretion? Accretion disks are universal. We see them everywhere around young stellar objects, stellar mass black holes, active galactic nuclei, white dwarfs, neutron stars, just to name a few. And we still don't really understand how accretion occurs, and they can be, the accretion process can be very different amongst these different mass ranges. Now, what makes young stellar objects, YSOs, and T-Tauri stars are a type of YSO, what makes these objects so useful to study accretion is that they're relatively close by and their disks are relatively large. And so they are the best studied accretion disks. They can be spatially resolved. And here I'm just gonna be focusing on accretion in YSOs, particularly T-Tauri stars for this talk. So then the disks around T-Tauri stars are also, they're not only accretion disks, but they're protoplanetary disks. So they're also important for understanding how planets form. So there's been an amazing diversity of planets that's been detected to date, one of the most striking results in the field of astronomy. So planets are diverse in size, composition, system architecture, and all of these properties had to be inherited from the protoplanetary disk out of which the planets formed. Now, the possible connection between accretion and planet formation is that young stars have variable high energy radiation fields generated not only by the star, but also the accretion process onto the star. And it's not clear how or if the variability of accretion and hence the accretion luminosity, the radiation on the disk from the accretion process, how that can or if it does affect the disk heating and chemistry. And then how would this subsequently affect the planet formation process? So there may be a link that remains to be seen. We're still in the very early stages. And this is one attempt, what I'll be talking about, to try to connect the star and the disk. And then perhaps in the future, there can be more work about connecting variability to planet formation, but still in the early stages. Okay, so there's a lot that we don't understand about protoplanetary disks, but this slide is a nice summary of what do we know about protoplanetary disks. So these disks are made up of dust and gas, so about 99% gas, and that's the brown shaded area in the slide. So that's a mix, that's dust and gas mixed in the disk. And then we have dust grains in the upper layers of the disk. In the upper atmosphere, they collide, they stick, they grow, they settle to the disk midplane. And then we think the higher density of solids in the disk midplanes facilitates grain growth and planetesimal growth and planet formation. We also see evidence for snow lines in disks. Here, just the water snow line is highlighted, but all the volatiles should have snow lines in the disk. And we think snow lines are another place in the disk that leads to overdensities of grains and would facilitate planet growth, grain growth and planet formation. And then there are a lot of processes we don't understand, like turbulence. How does material from the disk propagate inwards and then accrete onto the star? That's still a big question. And then there's a lot of interesting chemistry that happens in the disk that's linked to the temperature, the disk temperature structure. So closer to the star and the upper layers of the disk are the hottest, shown here in red. And then as you get further from the star and deeper into the midplane, the temperatures drop, and that's noted here in blue. Okay, so focusing now on the innermost part of the disk. Once you get to a temperature of roughly 1400 Kelvin in the disk, the dust sublimates, and you just have gas that keeps moving inwards towards the star. And that's represented here by this greenish transparent region. Now, these young stars have strong magnetic fields, and they truncate the gaseous disk, and material is channeled along the magnetic field lines onto the star, forming an accretion shock on the stellar surface. And I'll be talking about this in more detail, since I'll be talking a lot about accretion variability. But I just wanted to give you a quick overview of where this stands with respect to the rest of the disk, because I'm going to be focusing going forward on just the innermost part of the disk for the rest of the talk. Okay, so for the rest of the talk, I'll be focusing on just the innermost part of the disk. And these are regions that cannot be traced by any current imaging. So for example, this is 0.1 AU from the star at a distance at about 140 parsecs or so for where there are many disks. So I'll be talking about how can we use the variability, the multi-wavelength variability, which is tracing the star in the innermost part of the disk, to try to get an image, a picture of what's going on in the inner disk. And I've structured the talk along these three questions. The first serves as an intro, a quick recap of the field. What do we know about accretion variability in young systems? I'll spend most of my time with the second question. What do we learn from simultaneous multi-wavelength data? Telling you about our pilot study of one T-Tauri star. And then lastly, what are the plans to expand in the future accretion variability work? So things that are ongoing and things that are planned. Okay, starting off with the first question, what do we know about accretion variability? So first, a little bit more detail about how accretion proceeds in these young systems. Again, now focusing on like 0.1 AU from the star. So here in this schematic, this is scaled to interest, zooming in on the innermost part of the star disk system. And this is about 1 milliarc second for a frame of reference. So let's see. So this is the disk, which I showed before. It goes out to hundreds of AU. This is where the dust sublimates, and then you just have gas going inwards as the material and for some perspective, these young stars have magnetic fields of about 1 to 2 kilogauss. So we think that's strong enough to truncate the inner gas disk, and that accretion happens onto these young stars via the magnetosphere. So while the material is traveling in along the accretion flow, along the magnetic field line, we get broad emission lines. We see these in the optical and near infrared. So H alpha, bracket gamma are very popular accretion indicators that are used in these young systems. And then once the material impacts the surface of the star, it forms an accretion shock, which is shown here as this little light blue band. So this accretion shock emits as a very, the accretion shock has temperatures of about 8 to 10,000 Kelvin. So it peaks in about the near ultraviolet wavelengths. So for young stars, it's best to measure the accretion luminosity, the continuum from the accretion excess above the stellar photosphere in the NUV. And then also there are disk winds and jets that are launched from these systems. It's not clear exactly where they're launched from, but it's thought that they're connected to the accretion process. So evidence for these jets and winds from these disks. So this is an example of a famous jet from a young system, HH30, where the disk is edge on, and this is just an illustration to help your eye see where the disk is. So the disk is actually, you can't see it, it's the dark area because the dust, the small dust grains are very efficient absorbers of radiation. What you do see is light that is scattered off of the flared surface of the disk, which corresponds to this area here in the illustration. And then you see the beautiful jet that's launched roughly perpendicularly from the disk. And these jets and these young systems have velocities of about 100 to 1,000 kilometers per second. And this figure shows the connection between accretion onto the star and then ejection from the system. So these are plots of the mass loss rate in the wind and the mass accretion rate onto the star. And there's a correlation between the two, where the mass loss rate is measured to be about 10% of the mass accretion rate. And this has been confirmed. This was found in the in the 90s, and then it's been confirmed with every study that's followed this up until today. And I'll come back to this relationship much later on in the talk. Okay, and then I just want to show a recent confirmation that accretion in T-Tauri stars occurs via the magnetosphere. So the field had accepted this paradigm many years ago, but the first observational confirmation of this came out, I forget exactly when, I think it was like in the summer of 2020. But so these results are spectrointerferometry of TW Hydra, which is the closest protoplanetary disk at about 60 parsecs. And these were observations of bracket gamma, which is a line that originates in the accretion flow. And what they found was that they could place this line, which is shown here in red, as coming from a radius of 3.5 stellar radii, which is well within the inner edge of the dust plus gas disk, which is measured to be at 7.5 stellar radii. So this was the first observational confirmation that bracket gamma, which is thought to be linked to the accretion flow onto the star, is coming from a compact area that agrees with what we expect to see from a compact magnetosphere. Okay, so now how do we actually measure accretion rates? Because throughout the presentation, I'll be talking about accretion variability. So like I said, the accretion shock on the star, it leaves a continuum in the NUV, and you can measure the excess emission that you see from the system, the excess above what you would expect to see from the stellar photosphere in the NUV, and get an accretion luminosity. And you can use models to extract the accretion luminosity and convert that to an accretion rate. So the model that we use is depicted here. It's usually assumed that the shock is plane parallel and vertical. We think that's justified by a small extent. And we assume that the emitting region is a vertical column constrained by the magnetic field. And then, this is an idealized concept of a homogeneous accretion column. And we're assuming matter is falling in a dipolar magnetic field. But the actual accretion flow should be much more complex. They shouldn't be homogeneous in density or temperature. We use these simple models to try to interpret the observations, and they do a pretty good job. So on the right is an example of applying these models to data to get an accretion rate. So the gray are the data, and this particular T-Tauri star is BP tau. The blue is the emission you would expect for just a T-Tauri star without accretion. These are called weak T-Tauri stars. And you see there's a lot of excess in the NUV. That's all due to accretion. And then here we have two model components, the heated photosphere and then the pre-shock emission. And when you add up the emission you expect from the star and the accretion emission, you get the red line, which is the total. And here, the accretion rate, I think, is about 10 to the -8 solar masses per year or something, maybe a little bit higher, but the average accretion rate for T-Tauri stars is about 10 to -8 solar masses per year. All right, so the accretion process is observed to be highly variable. And variability is not new. T-Tauri stars were first discovered because they were variable, and they were discovered back in 1945. So I can't cover 75 years of work. So I'm just going to be focusing on what's most relevant to what I want to talk about today, which is accretion variability in the context of connecting it to multi-wavelength observations. So here, what I'm showing is HST spectra for 5 T-Tauri stars, and each of the different spectra is a different epoch. Some of them have 3, some of them have 8. But I've highlighted here in gray the NUV, which is where the accretion emission comes out. And you see that for all of them, the continuum is variable. So that's telling us that the accretion rate in all of these systems is changing. So every time we observe it, the accretion rate is a little different. Now, it's very expensive to get HST data to do this until another study that I'll tell you about at the very end. This was the largest HST survey of accretion variability for T-Tauri stars. So it's very expensive to get all the orbits you need with HST to do this. So what people usually do is they look at longer wavelengths, which are easier to get to the tail end of the accretion luminosity. So most of the accretion luminosity comes out in the NUV, but there's a little bit that's thought to come out in the optical. And also, of course, the ground-based U-band. So here on the left is an example of accretion rates measured. So each point is an accretion rate that's measured using ground-based U-band photometry. The bars are the range of variability. They're not uncertainties. It's the range of variability seen in the observations per target. So you see that there's a lot of variability when you measure accretion rates in these young systems. And the accretion rates were found to vary in this study on hour-long timescales and also week-long timescales. And then for the week-long timescales, since the typical rotation period the average rotation period of a T-Tauri star is about a week, the week-long variability is associated with rotational modulation of the accretion flow. Accretion variability is also seen in the optical. So there was a big study of 500 targets in NGC 2264, led by John Stauffer, where they looked at, in the studies called YSOVAR, and they looked at 500 targets in this region with a cadence of 8 minutes with Corot. And they were able to classify the different light curves they saw into 4 types of light curves, and 2 of those light curves were attributed to accretion variability. So the first on top here is stochastic, so irregular accretion variability, and then another kind of light curve called bursters, where you have the irregular accretion but also short bursts on top of that. And then most of the bursters had accretion burst with an occurrence rate of about 0.2 times per day, in addition to having longer timescale variability. So there has been some coordinated multi-wavelength work looking at the star disconnection before what I'll be talking about today. So on the left is an optical and mid-infrared study tracing accretion. So accretion is being traced in the optical, and the inner disk is being traced by the mid-infrared. And again, this is NGC 2264 from the same study, but just focusing on a few that had simultaneous Spitzer IRAC. And the Spitzer IRAC are the blue and the red, and the Corot are the black. And what you see here is that the dips in the mid-infrared and the optical occur at the same time. So what this is telling us is that there are clumps of material in or near that inner edge of the disk where the dust is sublimating that we think is passing through our line of sight to the stellar photosphere and obscuring the star plus the accretion. And then the idea could be here that maybe these are disk warps in the inner disk, or perhaps there's some dust that makes it into the accretion funnel flow and obscures the star. So that's one study, mid-infrared and optical. And then on the right is X-ray and mid-infrared, where the top panel is X-ray flux over time, and the bottom panel for each of these 4 panels, pairs of panels, is Spitzer-IRAC. And what this study found is that there's no strong evidence for a direct link between the X-ray and infrared variability for a sample of 40 disks in one star forming region. So this showed that there wasn't a strong connection between X-ray heating of the dust in the inner disk, so it wasn't significant. Okay, so that was a very quick overview of accretion variability and multi-wavelength studies and a sampling of the multi-wavelength studies to date. And now moving on to what do we learn from simultaneous multi-wavelength data? And in particular, the question that my team asked was, what can we learn about the star-disk-jet connection, harnessing the fact that accretion is variable. So for one target, we obtained 3 epochs of data separated by about a week with Chandra, HST, Spitzer, and the VLA. The observations were strictly simultaneous. So perhaps with maybe 5 or 10 minutes where they didn't overlap at the very beginning or end. So this was the first simultaneous observation of a T-Tauri star in these wavelength regimes. Now in the X-ray, we're trying to get at the stellar corona because we want to be able to constrain the high energy radiation from the star. In the UV, we're getting both with HST FUV and NUV. So the NUV, I told you, we can trace accretion. In the FUV, which I'll show you in a few slides, we can also get information about that gas that's in the innermost disk where there's no, where the dust has sublimated already. With Spitzer in the infrared, we wanted to trace the dust in the inner edge of the disk where the dust is sublimating. And in the centimeter, we wanted to trace the jet because we wanted to see, is there a connection between accretion onto the star and ejection from the system that we can detect. And then the target that we looked at for this study was the T-Tauri star GMrig. So we chose GMrig for many reasons. First, it's a low mass star. High mass stars are easier to observe, but the accretion mechanism in the high mass stars, we're not 100% sure yet if that's if the accretion is happening via the magnetosphere or boundary layer. So we wanted to do objects where maybe they're a little harder to do, but we understand how accretion is happening. It's also a transitional disk, which is shown here with these ALMA data. So that's a disk that has a very large hole. So here are the observations, here are simulations. When you look at the residuals between the observations and simulations, you don't get any, which is confirming that there's about a 20 AU radius hole in the disk. Because we didn't want to deal with what we saw in that Spitzer-Corot study, where you could have disk warps or dust close to the disk edge obscuring the star. We didn't want to deal with that. We wanted an object where it had a known jet, because for these later stages where the disk is no longer embedded in the cloud, so this is a much later stage than H30, which I showed earlier, the jets aren't as strong. There's only a handful of disks in this stage that have detectable jets. So we wanted an object that had a known jet. So here you see the jet in white contours and the photoionized part of the disk in the black contours. And these are centimeter VLA observations. We also wanted an object where it's been observed in the NUV and it's been seen to vary. So here are some HST spectra where it's known to be variable in the NUV. It also has some infrared excess emission. It's really hard to see here. I'll show it better in a couple of slides, but that 20 AU hole in the disk is almost completely empty of dust, but close to the star, there's still a small amount of ISM-sized dust. And we wanted that because so that we could trace the inner dust rim. And I'll show that more clearly later on. And then lastly, it's been detected in the X-ray. So it's a good target for us to observe in a relatively short time and get some good counts. Okay, so I'm going to step you through all the observations that we made, and there were a lot. So I'll step through one by one, make connections, and then I'll come back at the end and wrap it all up and remind you of the things we did, the different connections, because there are a lot. So we're trying to connect the star, the disk, and the jet. So first, what's going on with the mass accretion rate? What accretion rates do we measure? So we were very lucky that GMrig was caught during an accretion burst during our simultaneous set of observations. So what I'm showing here is all of the observations of GMrig that were taken with HST. Only the last three, epoch 6, 7, and 8, have the simultaneous data with from the X-ray to the centimeter. And lucky for us, this red spectrum here, which is clearly the highest state of GMrig, that was epoch 7. So we caught GMrig in a high state. So I'm going to gray out the other spectra now. The first of the three in our simultaneous study, epoch 6, that is yellow here. And also, I mean, I'll be referring to this as either the first, middle, or last epoch, or epoch 6, 7, or 8, just because there were 5 spectra before this. Okay, so yes, so the first of our 3 simultaneous data set has an accretion rate of about 0.6 times 10 to negative 8 solar masses pure, using the models I explained to you earlier. For the red, the accretion rate went up by a factor of about 3 to 2 times 10 to the negative 8, and it's the highest NUV ever observed for this object. And a week after that, in our last of the 3 epochs, it dropped back down. So what you're going to notice in the next few slides is that something is happening in all the wavelengths in this middle epoch, and I'll tie it back to the accretion. Okay, so but for now, remember in the middle epoch, something interesting is happening. The accretion rate went up by a factor of 3. Okay, so now what is happening to the gas and the dust in the innermost part of the disk? So let's start with the dust. Okay, so earlier I said that there's a little bit of dust left behind close to the star, and this shows it much more clearly. So the observations of GMrig are in blue. Here we have optical, JHK, Spitzer, IRAC, and then Spitzer IRS. The magenta, the broken line here is the stellar photosphere, and this gray line here is just what would you expect to see if there was a disk without a hole. So you see, just looking at the spectral energy distribution, the SED, there's a big drop in the mid-infrared. So in the infrared, you also see that big hole that's seen in the millimeter. But if you look closely for the first 2 Spitzer bands in the mid-infrared, it doesn't exactly agree with the photosphere. And also there's this very strong 10 micron silicon emission feature, which you can only get if you have small dust close to the star. So if we model the SED, we get this kind of structure where you have a big hole in the disk of 20 AU in radius. That's giving you this rise at the longer end of the SED here in the mid-infrared. And then close to the star, we get about a few lunar masses of optically thin dust that gives us the 10 micron feature and this small mid-infrared excess. And ISM dust is 0.005 to 0.25 microns. And this is all within 1 AU of the star. Okay, so when we did our study, Spitzer IRS was no longer functioning. So we only got the first 2 bands with Spitzer. So I just want to show you that there are these, those 2 bands, so a little bit above the photosphere. Okay, so here are the data. So 2 bands for epoch 6, 7, and 8. And epoch 7, you see that the infrared is at its highest state. And if you remember, the accretion burst was in the middle epoch. And so we interpret that the increase in flux in the mid-infrared is due to perhaps an increase of mass in the inner disk or an increase of mass that we're seeing in the inner disk, depending on our line of sight. So the first epoch and the last epoch are consistent with the flux level that I showed you in the previous slide. So I was able to apply the same models that we got the measurement from before, just apply them to epoch 7. And what we find is that there's a factor of 2.5 change in the dust mass that would give us this increase in the mid-infrared flux. So that's roughly consistent with a factor of 3 change in the accretion rate between the first and the middle epoch. So we can interpret this as the dust is tracing the surface density, and the accretion rate also traces the surface density. And so there's a connection between the dust that we're seeing and the accretion that we're tracing onto the star. Okay, so what is the gas doing in the inner disk? So here I'm using FUV spectra. So first I want to show you, for other T-Tauri stars, what does this FUV feature look like? So it's called the H2 bump. It's been found to trace gas in the inner 1AU of the disk, and it's shown here in red. And it's a combination of H2 emission lines and broad H2 continuum emission that's seen in several T-Tauri stars. So it's been seen, and if a T-Tauri star is accreting, it has this H2 bump. So it's in the community, it's pretty well known. So we searched for this feature in our data, and it's this little thing over here in between the very strong carbon-4 and helium-2 lines. So I'll zoom in on it here, and then you see that epoch 7, which is coded in red here, is higher than the other two epochs. And epoch 7, that's the middle epoch. So the middle epoch is higher. And the flux in this feature has increased by a factor of about 2. So that's roughly consistent with the factor of 3 change in the accretion rate and the factor of 2.5 change in the dust mass. So again, we think this is telling us that the surface density of the inner disk has increased, and the accretion rate onto the star is increasing as well. Okay, so we seem to have a connection between the star and the disk. What is the jet doing? So a reminder, GMrig is known to have a jet. These are VLA centimeter observations. These are high resolution 3 centimeter emission observations. We got low resolution 3 centimeter images of GMrig because the VLA didn't want to change its configuration just for us. Perfectly reasonable. So we only got fluxes, and I'll come back to why that's important in a little bit. So here are our VLA 3 centimeter fluxes. They're the circles. The squares are the accretion rate, just to draw your, to show you what the accretion rate is doing. But in the middle epoch, you also see that there's an increase in the 3 centimeter flux. And it looks like it's going back down, but still well within the uncertainties. So we think that so 2 points. This change in the middle epoch in the 3 centimeter emission is consistent with what I told you before, that the mass loss rate is about 10% of the accretion rate. I'll show you that in a couple of slides. Also, we attribute this change to changes in just the jet. Remember, we have low resolution data that traces the photoionized disk and the jet. And the reason we think it's tracing just the jet is because we got X-ray data, simultaneous X-ray data, and it doesn't change at all throughout the 3 epochs that we got the simultaneous data. So if the X-ray isn't changing, and we think the X-ray is what is photoionizing the disk, we're attributing all of that change in the centimeter emission to the jet. And also, it's interesting that the X-ray doesn't change because we can rule out changes in high energy stellar radiation as responsible for any of the changes we're seeing in the UV or the mid-infrared. Okay, so back to this point that the change that we see in the middle epoch is consistent with this well-known relationship that the mass loss rate is 10% of the mass accretion rate. So we did a rough calculation to show this. So here on the left is a plot of the radio continuum luminosity at centimeter wavelengths versus the outflow momentum rate. It leads to this empirical correlation on the right. And we can use this relationship to estimate the flux change that you would expect from a change in the outflow momentum rate. So we assumed the typically adopted jet velocity of 300 kilometers per second, that the mass loss rate is 10% of the accretion rate. We have the accretion rates from the HST data, so we can plug that in. And we get that the expected change would be 13 microjanskis, and the observed change that we see is 15 microjanskis. So it seems that it's roughly consistent with what we would expect from this well-known correlation, the change that we're seeing. Okay, so wrapping this up, tying it all together. So what we think is happening is that the surface density in the inner disk is increasing. So we see this as an increase in the mid-infrared emission from the dust and also from the FUV emission that's tracing the gas emission. So perhaps this is linked to not like a global change in the surface density in the inner disk, but perhaps there's some inhomogeneities in the inner disk. And then as the disk, the magnetic field is moving around, the disk is moving around, it passes by these inhomogeneities, these clumps, and it accretes more material. So not saying that it's like a global increase in the surface density, because the viscous timescale wouldn't be able to, that's not consistent with the viscous timescale. And then, okay, so if the surface density is increasing, there's like a clump in the disk that the field line has crossed. That would lead to more material loading onto the star. So the accretion rate would go up, as we see in the middle epoch. And then the increase in the mass accretion rate would lead to an increase in the mass loss rate. And we would see this as an increase in the 3 centimeter emission. So a caveat here is that we wouldn't expect that, so these observations are simultaneous. We wouldn't expect the jet emission to increase simultaneously, because it takes time for the material to travel along the jet. Instead, what it could be is that when we observe GMrig, we observed it once a week. Its rotation period is about 6 days. So it could be that we're tracing a minimum and a maximum to the accretion rate in our observations, and that this increase in the centimeter emission is linked to an accretion burst that happened like a week or two before, because we wouldn't expect it to be happening simultaneously. Okay, so then what would be connecting the star, the disk, and the jet? Presumably that'd be the magnetic field, which we think is leading to both the accretion onto the star and the ejection from the system. Okay, so like I said, this is a pilot study, and there are other opportunities to follow this up in the near future. So where do we go from here? And I'm going to overview some planned and upcoming accretion variability, or just some surveys that could be used to better understand accretion variability and make more multi-wavelength coordinated observations. Okay, so first we have Tess. The default cadence is 30 minutes, and we're going to get a lot of young stars because young stars are relatively bright. So this is currently active. Many T-Tauri stars have been observed and will be observed, and also many will be observed again. So there's also time for follow-up. There's the Vera Rubin Observatory with LSST, and that'll be an all-sky survey. So again, we will naturally be catching some T-Tauri stars because they're relatively bright. And then importantly, HST. So HST remains the best way to get accretion rates for T-Tauri stars. It's very difficult to do, as I mentioned earlier, because it takes a lot of orbits to get the data with HST. So luckily for us in the T-Tauri star community, those of us who are interested in accretion, the HST director has approved a discretionary UV legacy program with 1,000 orbits to obtain UV spectrum for pre-main sequence stars and high mass stars in a program called Ulysses. And this is the largest HST program ever executed, and half of the 1,000 orbits is for T-Tauri stars. So 500 orbits for T-Tauri stars, 100 of those orbits will be to monitor 4 targets for variability. And GMrig is one of those 4 targets. So the other 400 orbits will be used to study about 70 T-Tauri stars covering about 8 star forming regions. And the monitoring targets will be observed in 2 epochs. So for the first epoch, they'll be sampled 4 times per rotation period for 3 rotation periods. And in a year, they'll be followed up again with the same cadence. Now, why is this so important? Why is the NUV so important? So only HST is sensitive to all of the UV emission that's produced by the accretion shock, and ground-based facilities just aren't. So there's an example here, relatively recent example, looking at a T-Tauri star MY Loopy with HST versus X shooter, which is the next best thing to get as far into the UV as we can from the ground. So you see the X shooter spectrum is in red, HST is in black, and you see that they agree very well. We just can't get the NUV from the ground, which I've shown here in the gray shaded region. Now, the next plot I'm going to show you, before I show you it, I just want to get to the punchline because there's a lot of lines in that plot. The punchline is that the accretion rate that you get when you measure just the X shooter spectrum gives you an accretion rate of 10 to the -10 solar masses per year, which is the limit at which we consider if a star is accreting or not, or it's a very, very slow accretor. And if you model the HST spectrum, you get an accretion rate of 10 to the -8 solar masses per year, which is the typical accretion rate for T-Tauri stars. So it's a huge difference. So here's the plot that shows that. So here, the HST data are in black. The X-shooter data are not shown, but that's because they agree with the HST data. The red is a weak T-Tauri star template, and then the blue is the model. And this is a slightly different model than what we use. It's a slab model. And then the light blue, so the dark blue is the model, the light blue is adding the red and the dark blue. And you see that this model of 10 to the -8, this one goes through the HST data. It also goes through the ground-based part of the spectrum, the part of the spectrum you can get from the ground. And then this model, which is 10 to the -10 solar mass appear, still does a pretty good job of fitting the wavelengths you can get from the ground, but misses the HST spectra in the NUV. So this is just a demonstration of why it's so important to have a dedicated program like Ulysses while HST is still functioning, so we can really understand accretion in T-Tauri stars, because it's the best way to do it. All the other accretion rate estimates that we have are extrapolated from the NUV. So recognizing the importance of the Ulysses program, that it's very unique, that there's no planned successor to HST in the UV anytime in the near future, the community has gotten together to analyze this data set and to get coordinated observations to fully harness everything that we can out of this unique opportunity. So our name of our team is Odysseus. We're made up of about 60 young star experts from around the world, and we're going to be working together collaboratively to fully harness what we can from Ulysses. And then, you've seen this cartoon before. Here's just FUV. I didn't show a full FUV spectrum just so you see how many lines there are, how complicated it is, because FUV is also very important. My expertise is in the NUV and accretion, but FUV is also, we just can't get that without HST. So, and then here are the goals related to accretion, related to winds and jets, and then trying to connect the high energy FUV emission, which we think is very important for heating in the disk, to JWST and ALMA, which will be looking at the outer parts of the disk. So I think one of the most important contributions of the team is that we're working together to get other data to complement the HST UV data. So we have X-ray data. So the X-ray data is just planned for the 4 monitoring targets. And the goal is to try to get it as simultaneous as possible. And here you see the different observations and PIs. Optical near-infrared spectroscopy from the ground. So a very large legacy VLT program was approved, led by Carlo Manara. And also other facilities also have programs that are approved. And these will be, so these observations will be not only for the 4 monitoring targets, but also for the survey targets. And again, trying to observe before, during, and after. So trying to get things coordinated. And then also optical photometry is planned. And then as much as possible, HST is trying to coordinate their observations to overlap with Tess. Because Tess is observing many of the objects that are in this Ulysses survey. So stay tuned for results. The first paper is out. Manara et al. Forgot to cite it here. It's on AstroPH. That's overviewing the VLT component of the program. The first Odysseus results should be coming out this summer. And then, because the first part of the data was taken in November. So our first results are coming out. The next big set of data is coming out. It's going to be taken this summer. So then there'll be more papers coming out after that. So stay tuned for some results. Okay, so to summarize, I hope I've shown you that getting simultaneous wavelength data is very fruitful. It is very challenging to schedule, but it does help us to try to access and picture what's happening in the most part of the disk, which we can't do within the foreseeable future just because of the extreme high angular resolution that's needed to do that. And then we detected evidence for the first observational evidence for the connection between the star, the disk, and the jet. I'll leave my bullet points there, and just stay tuned in the future for more results from the Odysseus team using the Ulysses data set from HST to further understand accretion in these systems. Thank you very much.
Wow, Catherine, thank you very much. On behalf of everyone, a round of applause, which is always challenging virtually. But that, wow, it's a lot of very, very interesting science. It's an amazing program. I imagine there'll be a few questions. So would anyone like to start us off with a question for Catherine? Or while you're thinking, I will ask there's a question from Lynn in the chat. Can you see that, Catherine? Or?
Yes. So how can the study of accretion variability lead to the understanding of the diversity in the planets formed in the disks? Yeah, so we're in the very early stages of that. So the idea is, can the accretion variability lead to changes in the temperature of the disk or the chemistry of the disk? And if so, what ranges of accretion, like would we need huge accretion bursts? So like, for example, if we need huge accretion bursts to affect the temperature and chemistry in the disk, what would those changes be? And at what stage would they be? Because the stage that I talked about, the accretion bursts are pretty small, even though they look big in the figures, but the biggest changes in accretion happen in an earlier stage called the FU-ORI stage, where, and then there's some recent evidence from other wavelengths suggesting that planet formation happens earlier than the stage where we have the disk around the T-Tauri star. So if the planets are forming much earlier, when there's these huge accretion bursts occurring, and these big changes in luminosity, which would presumably maybe have changes in the chemistry and the temperature of the disk, what would the effects be on the planet? So we're still in the very early stages of trying to figure that out. So starting with the T-Tauri stars, which are easier to study because we can look at them, you know, like I showed here, like over a few weeks, and see the changes in the variability. We can see if that causes changes. Maybe it does, maybe it doesn't. We would need a dedicated ALMA observations to be able to figure that out. And I do have a data set and we're looking at it right now. So we're still trying to figure that out. But then the real question is with the FU-ORI stage, where the accretion bursts are much bigger, that's where you would expect to see the biggest changes, but you can't catch those. Those are unpredictable. So it's really hard to be able to catch it and like make the coordinate observations to see if there's an impact on the chemistry and the temperature of the disk. So still very early stages, but yeah, thanks for the question.
Okay, anyone else? Okay, so maybe I'll ask my question then at this stage. So the program on AUO was a kind of fantastic data set to sort of investigate this stuff, and some really nice results coming from it. I was wondering, seeing as you then going to do kind of re-observe AUO and another target with the Odysseus Ulysses, what did you learn from the first set of observations that you might kind of change or do kind of optimize for the second set?
Yes, a lot. So the GMrig observations are planned for this September, October, and then they will be repeated in a year. TW Hydra is being observed this week. And then there's 2 BP Tau, which I showed earlier as the sample object for the fitting, and RY loop will also be observed this summer. So getting simultaneous X-ray data is great, especially high resolution spectra. So that's hopefully all set, and hopefully that'll work out. So that's great. Yeah, and then like getting the VLT data, so getting the X shooter data at the same time, getting H alpha. So with there's also Espresso that's been approved, and I think also UVES, which will get like line profiles. So we're also going to get line profiles, which is another way of tracing accretion, but also winds from the system. There's no plans currently to do the millimeter or the centimeter again. It's just very challenging to do these observations, and it's not clear if the changes, you know, because you're kind of you're kind of hoping that there'll be a change big enough to lead to a change that you see. So asking for like, you know, can we get 3 weeks worth of daily observations? That's a lot. So we don't have planned any millimeter or centimeter coordinated observations like I showed in the pilot program, but we are hoping to get a survey of the objects, or putting in a proposal to get a survey of the objects so we can get more information like inclinations, disk masses, so we can start to make connections to the outer disk. Yeah, so I would say that working with many more people is much more helpful because many more people can like strategize and take different parts of the project, because doing, you know, and organizing this in simultaneous was really hard. So we're not going for simultaneous except for the X-ray data, because HST and Chandra, they tend to communicate really well with coordinating simultaneous things. But for the other things, we're working on coordinated because it's just so hard to get simultaneous. Yeah, so I would say that now we know the data is coming in, we have more time, we have more people we can recruit. And so I think this is going to be much more impactful, and I think we're going to get more out of it. It's just a matter of like, if the weather cooperates, and HST with the TW hydro observations, it's, you know, you heard, maybe some of you heard, it stopped working last week, and it was the day before it was supposed to start TW hydro. So then we had to cancel some things and shuffle some things. So even like, you know, when you plan for the best and even with space telescopes, sometimes things don't work out. So there's always that caveat, like you plan for the best, but you know, things might get upturned.
Yeah, I think that's always going to be the case, no matter how well you.
Yeah.
Cool. Yeah, thanks. Really interesting. Okay. Any other questions? All right, Tom.
I've gone if no one else does. So quite rightly, you're targeting sort of you know, classical or weak-line T-Tauri stars. So you've got an isolated star and disk. Are there any plans to look at sort of other types of systems like accretion onto binaries, or, you know, there's sometimes things where the disks are perturbed externally, so either an internal or an external binary that's affecting the accretion rate, maybe? Yeah, I'm thinking like RW Origo, where there's been that flyby and it's, you know, got a jet that's really powerful, for example.
So, you know, we, in selecting the targets for Ulysses, we purposely tried to avoid binaries because we just didn't want to deal with the complications of, you know, which objects is the accretion coming from. But of course, you know, you can't avoid binaries. So already in the initial sample, which is Sigma Ori and Orion, I think like 3 or 4 of the targets with the high resolution of imaging of HST were revealed to be binaries that were previously unknown. So there'll be some binaries in the sample, but they'll be close binaries because we purposely try to avoid anything known binaries, and usually the known binaries are the ones that are like more separated. Yeah, so sorry for the people that are really interested in like dynamics and interactions. We were trying to avoid that and those complications.
Yeah, I think that was a sensible thing to do. It's just, yeah, once you have a better handle on the sort of accretion onto single stars, then that would be, you know, it's an interesting next step, I think, to see how it differs, especially as these things often have crazy jets.
Yeah, definitely. So RY Loop, that's one object that was selected for the monitoring that has like, it has a jet and it has a wind. So there's a lot of complicated stuff going on with that one. And then hopefully HST is around for many more years after the program, and there can be follow-up studies.
Any other questions?
I have a quick, really technical one, but if someone else wants to ask something, then they should let themselves known, so I'm not hogging questions. If not, it was a very quick one, which is about how you're measuring the accretion rate from the H2 emission in the UV. Is that from the lines or from the continuum that you get that?
Yeah, so all the accretion rates I talked about were coming from the continuum. One of the goals of the Odysseus team is to be able to reproduce the FUV and NUV lines, which hasn't been done before, using combining the accretion shock model and also the accretion flow model. So that's something that's in the works, but we haven't done yet.
Thank you.
I have a kind of related question. So towards the end, you were looking at one of the systems that had HST spectra and also sort of ground-based X-shooter spectra, and the accretion rates you got between the two were a little bit different. Is that sort of just I guess sort of how widespread might that kind of be in terms of looking at with accretion rates with X-shooter? Could it be just time variability, or are the X-shooter spectra kind of below a certain accretion rate just meant to do?
Yeah, so I think we're going to figure that out with this sample, because for all the objects, X-shooter is planned, coordinated with the HST observations. So then the idea is, can we find a correlation between the two? Like, for example, is it going to be like a systematic offset that the accretion rates from the NUV are always X times higher than the accretion rates you get from fitting the optical data? We also are going to get lines like H alpha, I think bracket gamma, I'm not sure. But we can also measure accretion rates with the lines and see. So yeah. So like our preliminary work finds that the accretion rates from the NUV with the data set tend to be higher than the ones measured from the optical in the continuum. And then the next question is, when we have the entire sample, can we come up with some calibration to try to get around that, especially once we can no longer access the NUV?
Yeah, cool. Sounds like you've got a good plan to
yes. So it's like, we're very excited to have this data, but it's also very stressful because we're starting to realize we really do need the NUV, and it's going to be going away soon. So, but at least we have the data. We can try to figure out what we can now.
Cool. Okay. Any final question for Catherine? Okay, then on behalf of everyone, Catherine, thank you very much again for a really excellent talk. Very interesting questions, answer, discussion. It was really great.
Yeah, no, thank you for the invitation, and thank you for
everyone. Cool. So